Right now, the space between the stars surrounding you sits at a temperature of minus 454 degrees Fahrenheit. That is just a few degrees above the coldest anything can ever be. Scientists confirm that the average temperature of the universe hovers at 2.7 Kelvin, a number set by the fading afterglow of the Big Bang itself. But here is what most people get wrong. Space is not cold the way winter is cold. There is no frozen air, no icy wind, no chill you could feel on your skin. The cold of space is something far stranger and far more terrifying. It is the absence of almost everything: heat, matter, energy, and it dominates 99% of all existence. If you enjoy journeys that completely reshape how you see the universe, do me a small favor and hit that like button and subscribe. It genuinely helps this channel grow and lets me keep making these deep dives for you. Make yourself warm and comfortable as we journey together to find out just how cold space really is. Let's begin. Ask anyone how cold space is, and they will give you an answer without hesitation. Freezing. Absolute zero. Colder than anything on Earth. They will say it with confidence because the answer feels obvious. Space is dark, empty and lifeless. Of course it is cold. But that confident answer is wrong. Not slightly wrong, fundamentally wrong. The question itself contains a hidden trap that most people never notice. And the real answer is far stranger and far more unsettling than a simple number on a thermometer. To understand why, we have to carefully take apart everything you think you know about temperature, about cold, and about the nature of emptiness itself. Because the universe does not behave the way your intuition suggests. Not even close. This misunderstanding runs so deep that even well-educated people carry it without ever questioning it. Students are taught that space is cold. Documentaries describe a freezing void between galaxies. Science fiction films show astronauts instantly turning to ice when exposed to vacuum. All of this builds an image that is, at best, an oversimplification and at worst, deeply misleading. The true physics of temperature in a vacuum is one of the most counterintuitive ideas in all of science. And once you begin to see it clearly, it changes how you understand everything from how spacecraft survive in orbit to how the universe itself will ultimately evolve. Here is the problem. When you say something is cold, you are describing a sensation. You are talking about heat leaving your body and entering the surrounding environment. Step outside on a January night in Minnesota, and the air seems to attack you. Molecules of nitrogen and oxygen collide with your skin billions of times each second. Each of those collisions carries away a tiny fraction of your body heat. Your nerve endings register this steady loss of energy and send a signal to your brain: cold. That experience is so universal, so deeply embedded in human biology, that we instinctively treat it as a property of the environment itself. We say the air is cold. We say the water is cold. We say the metal railing is cold. But what we really mean is that these substances are drawing heat away from our bodies faster than we can replace it. Cold is not a thing in itself. It is the absence of something. It is what we experience when energy flows away. And this distinction matters far more than it first appears, because it reveals a fundamental flaw in how we ask the question about space. We ask, how cold is space, as though space were a substance with its own measurable temperature, like asking how cold the ocean is, or how cold the Arctic wind might be. But space is not a substance. The vast regions between stars are not filled with anything resembling cold material. They are filled with almost nothing at all. Now imagine removing everything. Remove the air, remove the water, remove every molecule of gas, every grain of dust, every atom of matter across millions of miles in every direction. You are left floating in the vacuum of deep space. Nothing touches your skin. No particles collide with your body. There is no medium to carry heat away through contact. So what temperature is it? The answer is, the question itself begins to lose its meaning. Temperature, in the way humans experience it, requires matter. It is a measurement of how fast particles move in a gas. Temperature reflects the average kinetic energy of molecules moving in random directions. Hotter gas means faster molecules. Cooler gas means slower ones. When those molecules collide with your skin, faster ones transfer more energy than slower ones. That is why hot air feels hot and cold air feels cold. It is, at its core, a story of motion and collision at the atomic scale, a process that requires something to exist and interact. But in space, that something is almost entirely missing. In the vacuum of space, there are no molecules, or more precisely, so few that the concept of temperature begins to lose its usual meaning. A single cubic centimeter of air at sea level on Earth contains roughly 25 billion molecules, that is 25 followed by 18 zeros. Every breath you take draws in this unimaginable swarm of particles. By contrast, a cubic centimeter of interstellar space might contain just one atom, sometimes even less. The density is so low that calling it a gas barely makes sense. Under these conditions, a conventional thermometer would have nothing to measure, because there is simply not enough matter to transfer energy in any meaningful or detectable way. And this is where the common understanding begins to break down. Space is not cold in the way a freezer is cold. A freezer is filled with cold air, slow-moving molecules that constantly collide with objects in steadily pulling heat away through direct contact. Space does not behave like this. There is almost nothing there to press against you. Nothing to carry heat away through touch. If you placed a thermometer in deep space, far from any star or planet, it would not be measuring the temperature of space itself. It would read its own temperature, and that temperature would depend entirely on the radiation the thermometer absorbs and emits. The instrument becomes the subject of its own measurement. It tells you about itself, not about the void surrounding it. This leads to a crucial distinction that most people are never taught. There are three ways heat moves from one place to another, and understanding all three is essential if we want to make sense of temperature in space. The first is conduction. Place your hand on a metal countertop, and heat flows directly from your warmer skin into the cooler metal through physical contact. Molecules in your hand vibrate, transferring that energy to the molecules in the surface. It is the most intuitive form of heat transfer, but it depends entirely on contact and on the presence of matter. Metal feels colder than wood at the same temperature because it draws heat away from your skin more efficiently. Your brain interprets that faster energy loss as a lower temperature, even though both materials may be identical in actual measurement. In space, conduction is almost irrelevant. There is nothing to touch. No surface pressing against you. No medium to carry heat away through contact. The second mechanism is convection. Turn on a space heater in your living room and warm air rises while cooler air sinks, creating a circulating flow. This movement of fluid, whether air, water, or anything that can flow, transports heat from one place to another. Convection is what drives weather systems on Earth, shaping winds, storms, and ocean currents. But once again, it depends on the presence of matter. In the near-perfect vacuum of space, there is no fluid to circulate, no currents to form, no rising or sinking motion to redistribute heat. It drives ocean currents, stirs the atmosphere, and carries heat from the equator toward the poles. It is why a breeze feels cooling on a hot day, and why a fan can make a room feel more comfortable, even though it does not actually lower the air temperature. Convection depends on differences in density within a fluid, and fluids require matter. In space, convection simply does not exist. There is no medium to circulate, no air to rise or sink, No currents to transport heat from one region to another. The vacuum remains still and empty in a way that has no true parallel in everyday human experience. The third mechanism is radiation. Every object with a temperature above absolute zero emits electromagnetic radiation. Your body is radiating infrared energy right now, quietly and continuously. In all directions, the walls around you do the same, sending infrared radiation back toward you. The sun emits across a much broader range, including visible light, ultraviolet and infrared. This form of energy transfer does not require a medium. It travels through empty space at the speed of light, crossing vast distances without friction or resistance. Unlike conduction and convection, radiation does not depend on matter. It moves through nothingness effortlessly, and this single fact reshapes everything about how temperature behaves in space. It means that the thermal state of any object is not determined by the emptiness around it, but by the radiation it absorbs and the radiation it emits. The vacuum itself plays no active role. It does not warm and it does not cool. It simply allows energy to pass through. Now consider an astronaut performing a spacewalk in low Earth orbit. With the sun in view, the side of the suit facing it is exposed to an intense flow of energy, approximately 1,360 watts per square meter. That is approximately the energy equivalent of running a small space heater pressed against every square meter of illuminated surface. The suit heats up. Without active cooling systems, the surface temperature on the sunlit side can climb past 120 degrees Celsius, hot enough to boil water, hot enough to cause severe burns on unprotected skin. The astronaut's suit becomes an oven on one side, baked by the unfiltered intensity of a star 93 million miles away. Now consider the shadowed side of that same astronaut. The side facing away from the sun receives no direct solar radiation. It begins to radiate its own heat into the void, energy escaping as infrared photons streaming into darkness, with no incoming sunlight and thermal energy steadily leaving. The shadowed surface cools rapidly. In the permanent shadow of space, temperatures can fall below -100 degrees Celsius. Some measurements in deep shadow approach -170 degrees Celsius, cold enough to turn carbon dioxide into dry ice, cold enough to make steel brittle, prone to cracking under stress, cold enough to freeze human tissue solid in minutes. This creates an extraordinary contrast. A single astronaut in orbit can experience a temperature difference of nearly 300 degrees across their body, not because space itself has different temperatures in different directions, but because it has no temperature in the conventional sense at all. What the astronaut is experiencing is not hot space on one side and cold space on the other, but the presence of intense radiation in one direction and its near absence in the other. The suit responds only to energy, what it absorbs and what it emits, not to any surrounding medium, because there is no surrounding medium to speak of. This is what makes the thermal environment of space so alien and so dangerous. On Earth, the air acts as a buffer. It smooths out temperature differences. Step from sunlight into shade on a summer afternoon, and the air temperature changes only slightly, perhaps a degree or two at most. The molecules around you remain at nearly the same temperature whether they are in direct sunlight or not. Because convection is constantly mixing the atmosphere, wind carries warmth into cooler regions. Rising air lifts heat away from the surface and cooler air is drawn downward to replace it. The atmosphere behaves like a vast thermal blanket, redistributing energy and softening extremes. In space, none of that exists. There is no buffer, no mixing, no smoothing, no protective layer. Radiation alone creates extreme temperature differences across distances as small as the width of a human body. The Moon provides one of the clearest demonstrations of this anywhere in the solar system. Its surface has no atmosphere, no air at all. Not a single molecule stands between the ground and the vacuum above. When sunlight strikes the lunar equator during its roughly 2-week-long day, the surface heats to about 127 degrees Celsius, hotter than boiling water, hotter than most household ovens at their maximum setting. The regolith absorbs this energy directly, with nothing to moderate the input. But when that same region rotates into the equally long lunar night, temperatures fall to around minus 173 degrees Celsius, a swing of roughly 300 degrees on the same patch of ground, driven entirely by the presence or absence of sunlight. By comparison, Earth's surface, shielded by its atmosphere, typically experiences temperature variations of perhaps 50 to 60 degrees between the hottest days and coldest nights. Even in the most extreme desert environments, the moon's temperature swings are 5 to 6 times more extreme, simply because there is no atmosphere to soften the transition. The air that Earth takes for granted performs a thermal role so significant that removing it turns a planetary surface into a landscape of lethal extremes. But even these dramatic changes only describe the temperature of the lunar surface itself. They tell us nothing about the temperature of the space above it. A thermometer hovering 1 meter above the sunlit moon would not match the temperature of the ground beneath it. Instead, it would reach its own balance. It would absorb radiation directly from the sun, take in infrared energy rising from the heated surface below, and at the same time radiate its own heat outward into space. The reading it displays would depend entirely on its physical properties, its size, its color, how reflective it is, the angle it faces relative to the sun, even its exact position above the surface. Change any one of these factors, and the measurement changes with it. The space itself offers no temperature to measure, only the objects within it do. Temperature is a property of matter. Where there is no matter, the concept begins to lose its physical meaning and becomes more abstract. This is why spacecraft engineers do not think in terms of the temperature of space. Instead, they think in terms of thermal balance. A spacecraft is constantly absorbing energy from the sun, from light reflected off nearby planets or moons, even from the faint infrared glow of the cosmic background. At the same time, it is continuously emitting its own thermal radiation into the void. Its temperature is set by the balance between these two flows, energy coming in and energy going out. When they are equal, the system reaches equilibrium and the temperature stabilizes. If more energy comes in than goes out, the spacecraft heats up. If more energy leaves than enters, it cools down. Managing this balance is one of the most critical challenges in spacecraft engineering, and it has been since the earliest days of spaceflight. Engineers rely on a combination of multi-layer insulation, reflective surfaces, electric heaters and radiator panels to maintain stability. The International Space Station uses large radiator arrays, spanning roughly 2,500 square feet, to release excess heat into space. Without these radiators, the station would gradually overheat due to its own systems and the constant input of solar radiation. The 6 crew members generate body heat. The onboard computers produce heat. The lighting systems add more. Every experiment conducted inside the laboratory modules contributes additional thermal energy. All of this heat accumulates within a sealed structure floating in a vacuum, where no air exists to carry it away. The radiators solve this problem by facing away from the sun and emitting infrared radiation into the surrounding void. They function as the station's only means of releasing excess energy. Without them, internal temperatures would continue rising until equipment failed and conditions became uninhabitable. At the same time, parts of the station that remain in shadow require electric heaters to prevent freezing. Batteries exposed to long periods of darkness must be kept above critical temperatures, or their chemical processes begin to fail. Fuel lines can freeze. Optical instruments may crack due to thermal contraction. Seals can become brittle and lose their integrity. The station exists in a constant balance between overheating and overcooling, controlled by carefully managing which surfaces face the sun and how efficiently heat is radiated away. Flight controllers on the ground continuously monitor thermal conditions, adjusting the station's orientation and activating or deactivating heaters as needed during each 90-minute orbit. The thermal environment is not a secondary concern, it is one of the primary factors that determines crew safety and mission success. Every single day, this thermal management challenge reveals something deeper about the nature of cold in space. The real danger is not that space is uniformly freezing. The danger is that space does not respond to your temperature at all. It offers no insulation, no buffering, no moderation. Whatever radiation reaches you determines whether you heat up or cool down, and nothing in the environment steps in to balance the extremes. That is why transitions can be so abrupt. In orbit, moving from direct sunlight into shadow does not feel like stepping into shade on Earth. It is more like crossing a boundary between two entirely different thermal conditions. The change can span hundreds of degrees over a distance of just a few inches. There is no gradual shift, no soft transition. Even a small object, like a bolt on the exterior of a spacecraft, can have one side intensely heated while the other remains deeply cold, separated by less than a centimeter of material. And this indifference extends everywhere. The vacuum of space is not actively trying to freeze you. It is not drawing heat away in the way cold air does on a winter day. On Earth, cold air continuously removes heat through conduction and convection. Wind accelerates this process, creating the familiar wind chill effect. Space has none of that. There is no air, no movement, no mechanism working against you. Instead, space does nothing at all. It provides no warmth, but it also does not actively cool. It is thermally empty. Your body loses heat simply because it radiates energy outward, and nothing replaces that energy unless a source of radiation like the sun is present. So the cold of space is not an attack. It is an absence. Not a force acting on you, but a lack of anything that might protect you, in a very real sense. It is not the universe reaching in to take your heat, it is the universe offering nothing in return. Now consider what this means at larger scales. Forget astronauts and spacecraft for a moment. Think about the spaces between stars. In our region of the Milky Way, the average distance between neighboring stars is roughly 4 light-years. That is approximately 24 trillion miles of vacuum separating one sun from the next. 24 trillion miles, where no significant radiation source exists to warm anything. The starlight from distant suns is so diluted by distance that it contributes almost nothing. The inverse square law ensures that radiation intensity drops with the square of the distance from its source. Double your distance from a star, and the radiation reaching you falls to 1/4. Triple the distance, and it drops even further. At 4 light-years from the nearest sun, the radiation from that star is so faint it would barely register on the most sensitive instruments ever built. Any object drifting through that interstellar void, a rogue planet ejected from its system, a fragment of ice cast outward by gravitational encounters, or even a spacecraft traveling between stars would slowly radiate away its own heat, photon by photon, with almost nothing incoming to replace that lost energy. How cold would such an object become? It would continue to cool, steadily shedding thermal energy into the darkness. Over time, its temperature would fall past the freezing point of water, past the freezing point of carbon dioxide, past the boiling point of liquid nitrogen, descending further and further down the temperature scale toward a limit it can approach but never quite reach on its own. That limit is set by the only radiation field that exists everywhere in the universe without exception, the faintest and most ancient light in existence. A glow so weak that no human eye could ever perceive it, yet so uniform that it fills every cubic centimeter of the cosmos. This is the cosmic microwave background radiation, and it defines the fundamental temperature floor of the universe, any object left alone in deep space. Far from any star, far from any galaxy, shielded from every local radiation source, will eventually cool until it reaches thermal equilibrium with this cosmic background glow. At that point, the object absorbs exactly as much energy from the background radiation as it emits through its own thermal radiation. Its temperature stabilizes, it stops cooling, and the temperature it settles at is approximately 2.7 Kelvin. That is 2.7 degrees above absolute zero, minus 270.45 degrees Celsius, or minus 454.81 degrees Fahrenheit. 2.7 Kelvin is the closest thing the universe has to a baseline temperature. It is not truly the temperature of space itself, because space is a vacuum, and vacuums do not possess temperature in the strict thermodynamic sense. It is the temperature that any object will eventually reach if left alone in the void with no other energy sources. It is the equilibrium point, the resting state, the thermal default of the cosmos, and it is almost as cold as anything can possibly be. Absolute zero, 0 Kelvin, is the theoretical point where all thermal motion ceases. Atoms stop vibrating, molecules come to rest. Energy reaches its lowest possible quantum state. No physical process in nature has ever achieved absolute zero, and the third law of thermodynamics tells us that reaching it exactly would require an infinite number of steps, making it fundamentally unattainable. Even the most advanced cryogenic laboratories on Earth, facilities that cool atoms to billionths of a degree above absolute zero using laser cooling and magnetic traps, cannot reach true zero. The universe itself cannot reach it. But 2.7 Kelvin lies so close to that boundary that, on any human scale thermometer, the difference is almost imperceptible. The baseline temperature of the universe sits just above the coldest condition that physics allows. On a scale running from absolute zero to the surface temperature of the Sun, 2.7 Kelvin would appear almost indistinguishable from zero. It rests that close to the lower limit. To understand how extreme this is, consider familiar cryogenic benchmarks. Liquid nitrogen, the substance used to rapidly freeze biological samples, boils at 77 Kelvin. The cosmic background temperature is roughly 29 times colder than liquid nitrogen. Liquid helium, the coldest commonly used cryogenic fluid on Earth, boils at 4.2 Kelvin. The baseline temperature of the universe is colder even than liquid helium. The only way to reach 2.7 Kelvin in a laboratory is through specialized cryogenic equipment that costs millions of dollars and consumes enormous amounts of energy to maintain. The universe achieves it effortlessly, passively, across almost its entire volume, simply by being empty. On Earth, the coldest temperature ever recorded in nature was minus 89.2 degrees Celsius at the Soviet Vostok station in Antarctica on July 21, 1983. That corresponds to approximately 184 Kelvin, a level of cold that is brutal, even dangerous, capable of freezing exposed skin in seconds and turning each breath into a sharp, biting sensation. And yet, the background temperature of the universe is roughly 68 times colder than that Antarctic record. The comparison reshapes what we think of as extreme. Conditions that represent the absolute limit of cold on Earth begin to feel almost mild when placed alongside the thermal baseline of the cosmos. What we experience as severe cold would be closer to warm. By comparison, on a universal scale, The difference is not just large, it is so vast that human intuition about temperature begins to break down entirely. Our everyday experience of cold simply does not translate to these conditions. And even this number 2.7 Kelvin does not tell the full story. It is an average, a background, a lower boundary that emerges when no significant energy sources are nearby. Because the universe is far from uniform, it contains stars with cores reaching tens of millions of degrees, vast molecular clouds lingering at 10 or 20 Kelvin, accretion disks around black holes soaring past 1 billion degrees, glowing nebulae at thousands of degrees and planetary surfaces spanning nearly every temperature in between. The thermal landscape of the cosmos is not a flat plane at 2.7 Kelvin. It is a terrain of staggering extremes, with towering peaks of unimaginable heat separated by vast frozen valleys stretching across millions of light years in every direction. The question is not simply how cold space is. The deeper question is how much of space exists at that near absolute cold, and how much of it is warm enough to matter. And this is where the picture becomes more unsettling. The warm regions, the stars, the planets. The glowing clouds of gas are the exceptions. Rare. Scattered. Isolated pockets of energy suspended within an immense expanse of cold. Warmth is not the rule. Cold is the rule. It is the default state of almost everything that exists in the universe. But to understand why cold dominates so completely, we need to trace the origin of that 2.7 Kelvin background. It did not emerge by chance. The universe was not always this cold. Its temperature has been falling since the very beginning, and that process of cooling is, in many ways, the story of cosmic history itself. It begins nearly 14 billion years ago. In the earliest moments after the Big Bang, when the observable universe was hotter than the core of any star that has ever existed, what happened to that immense heat, where it went, and why so little of it remains reveals something fundamental about the nature of the cosmos. Roughly 13.8 billion years ago, the universe as we know it did not exist. There was no space, no time, no matter, no energy in any form that current physics can fully describe. Then something changed. The event we call the Big Bang was not an explosion within space, it was an expansion of space itself. Space came into existence and began stretching outward, carrying with it temperatures and densities so extreme that no experiment on Earth has ever come close to recreating them. In the first fraction of a second, the entire observable universe, everything you can see through the most powerful telescopes ever built, occupied a volume smaller than a single atom. The temperature in that primordial instant exceeded 10 trillion degrees. A number so extreme it has no true comparison in human experience. Every particle of matter and energy that would one day form galaxies, stars, planets, oceans, and living organisms was compressed into a seething point of unimaginable heat. And it is from this heat that the story of cosmic cold truly begins, because the universe has been cooling ever since. In the first second after the Big Bang, the temperature fell from trillions of degrees to roughly 10 billion degrees. That may sound like an immense drop, and it was. But 10 billion degrees is still far hotter than the core of even the most massive stars. At 1 second old, the universe existed as a blinding plasma of protons, neutrons, electrons, photons and neutrinos, all colliding with energies that would instantly destroy any structure we are familiar with today. Matter and radiation were tightly coupled in a chaotic, high-energy state. Photons could not travel freely. They moved only microscopic distances before colliding with charged particles and scattering in random directions. The universe was opaque. Light filled every region, but it could not propagate in any meaningful way. In every direction, there was only an intensely bright, impenetrable fog. During the first 3 minutes, temperatures dropped below 1 billion degrees, cool enough for protons and neutrons to begin combining into the first atomic nuclei. Hydrogen formed naturally. A single proton. Deuterium appeared when protons and neutrons fused together. Helium nuclei formed from combinations of 2 protons and 2 neutrons. Small traces of lithium emerged through slightly more complex reactions. This process, known as Big Bang nucleosynthesis, lasted only a few minutes. By the time the universe was around 20 minutes old, it had cooled too much for nuclear fusion to continue. The process effectively shut down. The proportions of elements were set approximately 75% hydrogen and 25% helium by mass, a ratio that observations of the oldest stars still confirm today. Even so, the universe remained extraordinarily hot for hundreds of thousands of years after the Big Bang. Temperatures stayed above 3,000 degrees Celsius, comparable to a blast furnace. Under these conditions, matter could not exist in stable atomic form. Electrons remained free, moving independently rather than binding to nuclei. And those free electrons played a crucial role. They were extremely effective at scattering photons. Every time a photon encountered one, it was deflected in a new direction, preventing light from traveling freely through space. Light was trapped, ricocheting through the plasma like a ball in a pinball machine with an infinite number of bumpers. Information could not travel through this fog. No structure could be seen. The universe was a uniform, glowing, opaque haze stretching in all directions. Then, approximately 380,000 years after the Big Bang, the universe crossed a critical threshold. The temperature dropped below roughly 3,000 Kelvin. At this point, something remarkable happened. Electrons finally lost enough energy to be captured by atomic nuclei. Protons captured electrons and became neutral hydrogen atoms. Helium nuclei captured their own electrons. For the first time in cosmic history, matter became electrically neutral. Physicists call this event recombination, though the name is slightly misleading because it suggests the electrons and nuclei had been combined before they had not. This was the first time atoms formed in the history of the universe. The consequences were immediate and dramatic. Neutral atoms do not scatter photons the way free electrons do. When the electrons became bound into atoms, the universe suddenly became transparent. The photons that had been trapped for hundreds of thousands of years were released, free to travel in straight lines across the cosmos for the first time. This moment is known as the surface of last scattering, and it represents the oldest electromagnetic signal the universe can provide. Every photon released at that time has been traveling through space ever since, carrying information about the conditions when the universe was less than 1% of its current age. Those photons are still moving today. They fill every cubic centimeter of the observable universe. They arrive at Earth from every direction in the sky, an omnipresent bath of ancient radiation that has been streaming through the cosmos for nearly 13.8 billion years. This is the cosmic microwave background, but those photons no longer appear as they once did. When they were first released, they were visible light orange-red photons glowing at roughly 3,000 Kelvin, similar to the light of a cooling star. If you could have been present at that moment and somehow survived, the entire sky would have glowed with a deep, dim red light. There would have been no darkness, no shadows, no contrast, only a uniform glow extending in every direction. Since then, the universe has expanded by a factor of roughly 1,100. Space itself has stretched, and every photon traveling through it has been stretched as well. This stretching increases the wavelength of light, and longer wavelengths mean lower energy. Lower energy means lower temperature. The original visible light photons from recombination have been stretched so severely over billions of years that they now exist as microwaves. Their wavelength has increased from less than a micrometer to over a millimeter. Their effective temperature has dropped from 3000 Kelvin to just 2.725 Kelvin. The entire sky still glows just as it did at recombination. But the glow has been shifted so far into the microwave spectrum that no biological eye could ever detect it. The cosmic microwave background is the afterglow of creation, dimmed and stretched by the expansion of space, until it became invisible to everything except purpose-built instruments. The discovery of this radiation is one of the great accidental triumphs in the history of science. In 1964, two radio astronomers at Bell Telephone Laboratories in Homedale, New Jersey, were using a large horn-shaped antenna for satellite communication experiments. Arno Penzias and Robert Wilson were meticulous scientists. They wanted their antenna to be as sensitive as possible, which meant eliminating every source of unwanted noise. They calibrated their equipment carefully. They accounted for radio interference from nearby New York City. They pointed the antenna away from known astronomical sources. They even climbed inside the horn and removed pigeon droppings, suspecting the birds nesting in the antenna might be contributing thermal noise to their signal. Nothing worked. No matter what they did, a faint, persistent hiss remained in their data. It came from every direction equally. It did not change with the time of day. It did not change with the season. It did not change when they pointed the antenna at different parts of the sky. The noise was perfectly uniform, perfectly constant, and completely unexplained by any terrestrial source they could identify. The signal corresponded to a thermal source at roughly 3.5 Kelvin, just a few degrees above absolute zero. Penzias and Wilson were puzzled, but they did not immediately understand what they had found. They spent months searching for an explanation. They had not been looking for cosmological signals. They were communications engineers trying to build a better antenna, not cosmologists searching for the origin of the universe. The connection between their mysterious noise and the origin of the universe came from a group of theoretical physicists working just 40 miles away at Princeton University. Robert Dicker, Jim Peebles, and their colleagues had independently predicted that the Big Bang should have left behind a faint thermal radiation filling all of space. They were in the process of building their own antenna to search for this signal when they learned that Arno Penzias and Robert Wilson had already detected it by accident. The realization was extraordinary. The persistent hiss in the Bell Labs antenna was not instrument noise. It was not pigeon droppings. It was not radio interference from human activity. It was the remnant heat of the Big Bang itself, the oldest light in the universe, arriving at a radio antenna in New Jersey after a journey spanning nearly the entire history of cosmic time. Penzias and Wilson had stumbled upon one of the most important cosmological discoveries since Edwin Hubble demonstrated that the universe is expanding. They were awarded the Nobel Prize in Physics in 1978. The initial measurement was crude by modern standards. Penzias and Wilson estimated the temperature to be around 3.5 Kelvin, with significant uncertainty. But their discovery opened the door to a new era of precision cosmology. Over the following decades, increasingly advanced instruments refined the measurement with remarkable accuracy. The first major leap came with the Cosmic Background Explorer, launched by NASA in 1989. COBE carried instruments specifically designed to measure the cosmic microwave background far more precisely than ground-based systems could. Earth's atmosphere interferes with microwave observations, absorbing and emitting radiation that contaminates measurements. A satellite operating above the atmosphere avoids this problem entirely. COBE delivered two groundbreaking results. First, it measured the spectrum of the cosmic microwave background and found that it matched the theoretical prediction of a perfect blackbody radiator with extraordinary precision. A black body is an idealized object that absorbs all incoming radiation and emits energy in a pattern determined solely by its temperature. The spectrum measured by COBE fit the blackbody curve so precisely that the data points were virtually indistinguishable from the theoretical prediction. It was the most perfect blackbody spectrum ever measured in nature, confirming that the radiation originated from a hot, dense and uniform early universe exactly as Big Bang theory had predicted. The temperature was refined to 2.725 Kelvin, with an uncertainty of less than 1,000th of a degree. COBE's second result was even more profound. The satellite detected tiny temperature fluctuations in the cosmic microwave background. The radiation was not perfectly uniform. Some regions of the sky were a few hundred thousandths of a degree warmer than average. Others were a few hundred thousandths of a degree cooler. These variations were incredibly small, on the order of 1 part in 100,000, but their significance was enormous. They revealed the primordial density differences in the early universe, the initial seeds from which all cosmic structure would eventually form. Regions that were slightly warmer at recombination were also slightly denser. Those denser regions had a slightly stronger gravitational pull over billions of years. This small advantage allowed them to attract surrounding matter, growing progressively denser until galaxies, clusters of galaxies, and the vast cosmic web emerged from what was once nearly uniform. The fluctuations in the cosmic microwave background are, in a sense, the imprint of quantum mechanics on the largest possible scale. In the first fraction of a second after the Big Bang, quantum fluctuations, the inherent uncertainty in energy at subatomic scales, created tiny variations in density. Then, during a brief period of rapid expansion known as inflation, these microscopic fluctuations were stretched to cosmic scales. What began as variations smaller than an atom expanded into structures spanning millions of light-years. The cosmic microwave background preserves a snapshot of those amplified quantum ripples. Frozen at the moment recombination made the universe transparent. After COBE, 2 more satellite missions pushed the measurements even further. The Wilkinson Microwave Anisotropy Probe, known as WMAP, launched in 2001 and mapped the cosmic microwave background with roughly 35 times the angular resolution of COBE. WMAP could distinguish temperature variations on scales as small as a fraction of a degree on the sky, revealing the detailed structure of primordial density fluctuations. The map it produced looks like an oval covered in splotches of slightly different colors, warm spots in red and orange, cool spots in blue and green. This map has been called the baby picture of the universe. It shows the cosmos as it appeared at 380,000 years old, billions of years before the first stars ignited. WMAP determined the age of the universe with unprecedented precision, establishing 13.77 billion years. It confirmed that ordinary matter, the atoms that make up stars, planets and human beings, constitutes only about 4.6% of the total energy content of the cosmos. Dark matter accounts for roughly 23%. Dark energy, the mysterious force accelerating cosmic expansion, makes up the remaining 72%. These numbers, extracted from the patterns in ancient microwave radiation, form the foundation of modern cosmology. Nearly everything we know about the large-scale properties of the universe comes from studying this faint, cold glow. The European Space Agency's Planck satellite, launched in 2009, refined the measurements further. Planck observed the cosmic microwave background at 9 different frequency bands with angular resolution and sensitivity that surpassed WMAP by another significant margin. The resulting maps are the most detailed images of the early universe ever produced. Planck refined the age of the universe to 13.798 billion years. It confirmed the background temperature first pinned down by Cope's Virus instrument at 2.725 Kelvin and mapped the tiny fluctuations around that average. With unprecedented precision, it measured the proportions of ordinary matter, dark matter, and dark energy with percent-level accuracy, and it revealed subtle patterns in the fluctuations that constrain theories about what happened during the first trillionth of a second after the Big Bang. 3 satellite missions, spanning 2 decades, transformed the cosmic microwave background from a crude detection into the single most informative observation in all of cosmology. A faint hiss that annoyed 2 radio engineers in 1964 became the Rosetta Stone of the universe. But what does all of this mean for the temperature of space? It means that the 2.7 Kelvin baseline is not just a number. It is a fossil, a thermal relic from a time when the universe was young, hot and filled with light. Every photon in the cosmic microwave background has been traveling since recombination. Each one carries a tiny packet of energy from an era when the cosmos was 3,000 degrees everywhere. Those photons have lost almost all of their energy to the expansion of space. They have been stretched, diluted, cooled from visible light to microwaves over 13.8 billion years of cosmic evolution. The 2.7 Kelvin we measure today is the exhausted remnant of a once blazing universe. And the cooling is not over. The universe continues to expand. As it does, the cosmic microwave background continues to stretch and cool. Every moment, the background temperature drops by an almost imperceptible amount. In the far future, billions of years from now, the temperature will be lower still. A universe twice its current size would have a background temperature of roughly 1.4 Kelvin. A universe 10 times larger would glow at just 0.3 Kelvin. The cosmic microwave background is like a fading ember, slowly dimming toward a darkness that will never quite reach absolute zero, but will continue to approach it over timescales far beyond the current age of the universe. This ongoing cooling reveals something fundamental about the thermal history of the cosmos. The universe was born hot, unimaginably hot. Every point in space was once a furnace that would have destroyed any structure, any molecule, an atom. But that heat was never meant to last. It was an initial condition, steadily diluted over time. The expansion of space acts like a cosmic refrigerator, stretching radiation to longer wavelengths and lower energies with each passing moment. The universe does not generate new heat on a universal scale. Stars produce energy locally, but they do so by converting matter into radiation, a process that will eventually run out as their fuel is exhausted. The total thermal budget of the cosmos was set at the Big Bang and has been declining ever since. Think of it this way. The Big Bang deposited an enormous quantity of thermal energy into a tiny volume. That energy has been spreading out as space expands, thinning across an ever-growing cosmic volume. The density of thermal energy decreases with expansion. Temperature drops. What was once a searing plasma capable of preventing atoms from forming is now a whisper of microwave radiation, so faint it required humanity's most advanced instruments to detect. The universe spent its thermal inheritance in the first few 100,000 years and has been running on fumes ever since. The uniformity of the cosmic microwave background also tells us something remarkable about the large-scale structure of space. The temperature is the same in every direction to a precision of 1 part in 100,000. A photon arriving from a point in the northern sky has almost exactly the same energy as a photon arriving from the opposite direction in the southern sky. Yet those 2 photons originated from regions of space that were separated by tens of millions of light years at the time of recombination. Those regions had no way to communicate with each other. Light had not had enough time to travel between them since the Big Bang. How did they end up at the same temperature? This is known as the horizon problem, one of the central puzzles of 20th century cosmology. The leading explanation, proposed in 1980 by physicist Alan Guth, is cosmic inflation. According to inflation theory, the universe underwent a period of extremely rapid expansion during the first tiny fraction of a second after the Big Bang. In roughly 10 to the power of minus 36 seconds, space expanded by a factor of at least 10 to the power of 26. Regions that had once been close enough to exchange energy and reach the same temperature were suddenly driven far apart by this expansion. By the time the cosmic microwave background was released, those regions were separated by distances too vast for light to cross. Yet they retained the thermal uniformity established before inflation pulled them apart. Inflation explains why the cosmic microwave background appears so remarkably uniform. The temperature was equalized before expansion spread it across the sky. The tiny fluctuations, those 1 part in 100,000 variations, represent quantum disturbances that occurred during inflation itself. Stretched to macroscopic scales by the rapid expansion, without inflation, the uniformity of the cosmic microwave background would be an inexplicable coincidence. With inflation, it becomes a natural consequence of physics operating in the earliest moments of cosmic history. The temperature fluctuations in the cosmic microwave background also encode information about the geometry and composition of the universe. The pattern of hot and cold spots is not random. It contains preferred angular scales that correspond to sound waves oscillating through the primordial plasma before recombination. These oscillations, called baryon acoustic oscillations, left a characteristic imprint on the distribution of temperature fluctuations. The angular size of the strongest oscillation mode reveals whether the universe is flat, positively curved, or negatively curved. Planck measurements confirm with high precision that the universe is geometrically flat, meaning parallel lines remain parallel over cosmic distances and the angles of a triangle sum to exactly 180 degrees. The acoustic peaks in the fluctuation pattern also reveal the density of ordinary matter and dark matter separately. The height and spacing of the peaks depend on how much ordinary matter participated in the sound waves versus how much dark matter provided gravitational scaffolding without interacting with photons. Fitting the observed peak pattern to theoretical models yields precise values for both quantities. Establishing that dark matter outweighs ordinary matter by roughly 5 to 1, this measurement, derived entirely from temperature fluctuations in ancient microwave radiation, agrees independently with measurements from galaxy rotation curves, gravitational lensing, and the large-scale distribution of galaxies. The cosmic microwave background serves as an independent witness, confirming the existence of a dark universe from a completely different era of cosmic history. All of these measurements depend on the extraordinary faintness of the cosmic microwave background. The radiation that fills the universe carries so little energy per photon that it contributes almost nothing to the thermal environment of objects in space. A spacecraft in orbit around Earth receives millions of times more energy from the Sun than from the cosmic microwave background. Even in the deepest regions of intergalactic space, far from any star or galaxy, the background radiation provides only enough energy to maintain an equilibrium temperature just above absolute zero. The ancient light that once filled the universe as a blazing plasma has been stretched into near-thermal insignificance by the expansion of space itself. It surrounds everything, it permeates everything, but it warms almost nothing. This is the central paradox of the cosmic microwave background. It is everywhere, yet its thermal contribution is negligible. It fills every point in space with radiation. Yet that radiation is so weak that it defines the coldest achievable temperature in the natural universe, rather than providing meaningful warmth. The afterglow of the hottest event in cosmic history has become the marker for cosmic cold. The fire that once blazed at billions of degrees now registers as 2.7 Kelvin. The universe cooled itself by growing. The cosmic microwave background also sets a fundamental limit on how cold anything in the natural universe can become. No object in space, no matter how isolated, how shielded, how far removed from any star or galaxy, can cool below 2.7 Kelvin through natural processes. The background radiation bathes everything in a minimum level of energy that prevents temperatures from falling further. In laboratory settings on Earth, scientists routinely achieve temperatures far below 2.7 Kelvin using active cooling technologies. Atoms have been cooled to billionths of a Kelvin using laser traps and evaporative technique. But those experiments require continuous energy input to maintain such extreme cold. The moment the cooling systems are removed, the atoms begin to warm again. In the natural universe, without artificial intervention, 2.7 Kelvin is the floor, the lowest temperature that any passive object can reach. This means that the cosmic microwave background performs two seemingly contradictory roles at the same time. It provides the faint warmth that prevents the universe from reaching absolute zero, and it defines the extreme cold that characterizes nearly all of cosmic space. It is both the universe's last trace of universal warmth and the reference point for measuring cosmic cold. Without it, space would be even colder, approaching absolute zero with nothing to establish a minimum thermal limit. With it, space settles at 2.7 Kelvin warmer than absolute zero, yet colder than almost anything humans have ever encountered outside of specialized laboratory conditions. The cosmic microwave background is fading. The universe continues to expand. The photons continue to stretch. In the distant future, the background temperature will drop below 2 Kelvin, then below 1, then into fractions of a degree above absolute zero. The afterglow of the Big Bang is slowly being extinguished by the relentless growth of space. One day, trillions of years from now, the cosmic microwave background will become so faint and so cold that no conceivable instrument could distinguish it from true emptiness. The last evidence of the universe's hot origin will vanish into the expanding void, leaving behind a cosmos with no memory of the fire that created it. But that future is unimaginably distant. Today, the cosmic microwave background still fills the universe at 2.7 Kelvin. It still encodes the history of cosmic evolution in its temperature and fluctuations, and it still defines the thermal baseline against which every other temperature in the cosmos must be measured. That baseline, however, tells only half the story. The cosmic microwave background describes what happens in the absence of local energy sources. It tells you the temperature of the void, the empty regions between galaxies where nothing shines and nothing burns. But the universe is not entirely empty. Scattered throughout the cosmic darkness are objects of extraordinary thermal intensity. Stars that burn at millions of degrees, nebulae heated by newborn suns, accretion disks that reach temperatures rivaling the earliest moments after the Big Bang. These structures create local thermal environments that deviate dramatically from the 2.7 Kelvin background, sometimes by factors of billions. The question now becomes how those extreme pockets of heat compare to the overwhelming cold. How much of the universe burns? And how much of it remains in darkness? The answer determines whether warmth or cold defines the true nature of the cosmos. And when the numbers are examined closely, the result is far more unbalanced than most people expect. Stars are the exceptions that reveal the rule. In a universe that defaults to 2.7 Kelvin, stars represent pockets of thermal intensity, so extreme they seem almost out of place. Our Sun has a surface temperature of approximately 5,500 degrees Celsius, while its core reaches around 15 million degrees Celsius. These values exist on a completely different scale from the cold that surrounds them, separated from the cosmic baseline by factors of millions. A star is not just warm. It is a sustained thermonuclear explosion, a sphere of plasma held together by gravity and powered by the fusion of hydrogen into helium at pressures and temperatures that have no parallel anywhere else in the natural universe, except in the hearts of other stars. Every star you see in the night sky is performing this same violent process. Converting matter into energy at rates that would seem impossible if they were not so common. The Sun converts roughly 4 million tons of matter into pure energy every second. Not 4 million tons of fuel burned into ash, 4 million tons of mass transformed into energy through Einstein's equation relating mass and energy. That energy radiates outward in every direction, crossing 93 million miles of vacuum to reach Earth in about 8 minutes. It warms our planet. It drives our weather. It powers photosynthesis. It sustains every living system on the surface of this world. And our Sun is not even an extreme example. It is a middle-aged, medium-sized yellow dwarf, unremarkable among the hundreds of billions of stars in the Milky Way. Larger stars burn far hotter, blue supergiants, like Rigel in the constellation Orion, shine with surface temperatures exceeding 11,000 degrees Celsius, roughly twice the temperature of the Sun's surface. Their cores can reach hundreds of millions of degrees, fusing not only hydrogen, but also helium, carbon, oxygen, and heavier elements in layered shells of nuclear reactions. The most massive stars known, those with more than 100 times the mass of the Sun, consume their fuel so rapidly that their entire lifetimes last only a few million years. Compare that to the Sun's expected lifespan of about 10 billion years. These massive stars live fast, burn intensely, and end in catastrophic explosions that can briefly outshine entire galaxies. At the other end of the spectrum, red dwarfs burn slowly and at lower temperatures. Their surfaces hover around 3,000 degrees Celsius, dim compared to the Sun, but still thousands of times hotter than the cosmic background. Red dwarfs are the most common type of star in the universe, outnumbering all other stellar varieties combined by an enormous margin. Roughly 70% of all stars in the Milky Way are red dwarfs. They are so faint that not a single red dwarf is visible to the naked eye from Earth. Despite being the most numerous objects in the stellar population, they burn their fuel so slowly that their lifespans extend into the trillions of years, far longer than the current age of the universe. Every red dwarf that has ever formed is still shining today. Not a single one has yet exhausted its fuel. Not one has died. These dim, enduring stars represent the most numerous thermal exceptions in the cosmos, each one a small source of warmth within the vast cold, and collectively, they will be the final sources of stellar heat the universe will ever have, long after massive stars have exploded. Long after stars like the Sun have expanded into red giants and collapsed into white dwarfs, red dwarfs will continue to burn quietly, faintly, alone as the universe grows darker. But stars are not the only sources of extreme heat. When matter falls toward a black hole, it does not simply disappear. It spirals inward through an accretion disk, a rotating structure of gas and dust compressed by gravity to such extremes that it heats to temperatures comparable to those of the early universe. The inner regions of accretion disks around stellar mass black holes can reach tens of millions of degrees. Around supermassive black holes, those found at the centers of galaxies, with masses of millions or billions of suns, temperatures rise into the hundreds of millions of degrees. The most extreme environment, found in active galactic nuclei and quasars, can approach 1 billion degrees or more. These are among the hottest sustained conditions in the modern universe, exceeded only briefly in events like supernova explosions or high-energy particle collisions. Supernovae themselves produce some of the most extreme temperatures ever reached since the early universe. When a massive star runs out of nuclear fuel, its core collapses in less than a second. The core, with a mass comparable to our Sun, is compressed into a sphere roughly the size of a city, collapsing at speeds approaching a quarter of the speed of light. The collapse rebounds off the dense core, sending a shock wave outward through the star's outer layers, releasing an immense amount of energy, so much that, for a brief moment, it can rival the total luminous output of entire galaxies in the form of neutrinos alone. The temperature at the collapsing core reaches roughly 100 billion degrees for a brief, violent instant. That is hotter than the interior of any stable star, hotter than any accretion disk, hotter than the universe has been at any point since the first second after the Big Bang. In that instant of core collapse, a dying star briefly recreates conditions that existed when the cosmos was less than 1 second old. The explosion that follows can outshine the combined light of every other star in its host galaxy for weeks, releasing more energy in a few seconds than the Sun will produce over its entire 10 billion year lifetime. And then it fades. The heat disperses. The expanding remnant cools over thousands of years, eventually blending into the cold interstellar medium. The thermal violence is extraordinary, but short-lived. A match struck in a dark room that illuminates everything for a moment before darkness returns. Stellar nurseries present a gentler, but still striking, contrast. Nebulae, the vast clouds of gas and dust where new stars are born, contain regions spanning dozens of light years that glow at temperatures ranging from 10,000 to 20,000 degrees. These emission nebulae are heated by ultraviolet radiation from young, massive stars embedded within them. The Orion Nebula, visible to the naked eye as a faint patch below Orion's belt, contains gas heated to roughly 10,000 Kelvin across a region more than 20 light-years wide. Surrounding these hot, ionized regions are colder molecular clouds, where temperatures fall to just 10 or 20 Kelvin, barely above the cosmic background. Star formation occurs in these coldest zones, where gas can collapse under gravity without being torn apart by thermal pressure. The process is both counterintuitive and elegant. The coldest regions of a galaxy are the very places where its hottest objects are born. Stars emerge from darkness, and that darkness is essential to their creation. Even within our own solar system, the range of temperatures is extraordinary. Venus, wrapped in a dense carbon dioxide atmosphere that traps heat with extreme efficiency, maintains a surface temperature of roughly 465 degrees Celsius. That is hot enough to melt lead with ease. Hot enough to destroy any spacecraft that has landed on its surface within mere hours. Meanwhile, in the outer solar system, Neptune receives so little sunlight that its upper atmosphere hovers around -214 degrees Celsius. Pluto, in the distant reaches of the Kuiper Belt, averages -230 degrees Celsius. The difference between the hottest planet in our solar system and the coldest known dwarf planet spans nearly 700 degrees. Yet even Pluto, at its most extreme, remains significantly warmer than the cosmic microwave background. It still receives enough distant sunlight to keep its temperature roughly 40 degrees above the universal floor. Remove the sun entirely and Pluto would cool further, gradually descending toward that final 2.7 Kelvin equilibrium over thousands of years. All of these thermal extremes, from the hottest accretion disks to the coolest red dwarfs, from supernovae to planetary surfaces, share one essential characteristic. They are vanishingly small compared to the space between them. And this is where the question of temperature begins to take on a deeper, more unsettling meaning. These sources of heat are real. They are powerful. They are spectacular. But they are also incredibly small, almost insignificant when compared to the vast emptiness that surrounds them. Consider the sun. It is immense by human standards. You could fit approximately 1.3 million Earths inside it. Its diameter spans roughly 865,000 miles. It dominates our local environment, holding planets in orbit across billions of miles of space. And yet, the nearest star, Proxima Centauri, lies about 4.25 light-years away, roughly 25 trillion miles. If you scaled the Sun down to the size of a ping-pong ball, Proxima Centauri would be another ping-pong ball placed about 720 miles away. Between those two tiny points lies almost nothing. 720 miles of empty space. Two small sources of warmth separated by an immense void vastly larger than either of them by a factor of tens of millions. You could place tens of millions of suns between them and still have empty space left over. Each one would be a blazing furnace of nuclear energy. Yet the space between them would remain cold, dark and nearly empty. This is not unusual. It is typical. It is the standard spacing of stars in our region of the galaxy. Even in denser regions, such as the central bulge of the Milky Way, stars remain separated by distances far greater than their own size. Stellar collisions are extraordinarily rare, precisely because stars are so small compared to the vast spaces they occupy. Scale this up to the galaxy, and the proportions become even more extreme. The Milky Way contains an estimated 200 to 400 billion stars. That sounds like an enormous number until you consider the volume they occupy. The galaxy spans roughly 100,000 light-years across and 1,000 light-years thick. Its total volume is approximately 8 trillion cubic light-years. Divide that volume by the number of stars, and each one occupies, on average, a region of roughly 20 to 40 cubic light-years of mostly empty space. Stars are separated by distances so vast compared to their sizes that the galaxy is almost entirely vacuum. If you could observe the Milky Way from the outside, with enough resolution to see individual stars, you would mostly see darkness, interrupted by scattered points of light, like a handful of fireflies drifting inside a football stadium at night. The stadium is real, the fireflies are real, but what defines the scene is the darkness between them, not the lights themselves. The thermal consequence of this spacing is profound. Each star warms only a small region around it, a limited sphere of influence where its radiation still matters. Beyond that, its effect fades rapidly into the background of the cosmos. The Sun's thermal influence extends only a few hundred astronomical units before it becomes indistinguishable from the surrounding cold. The habitable zone, the narrow region where liquid water can exist, lies between roughly 0.95 and 1.7 astronomical units from the Sun. That band is about 70 million miles wide. It sounds vast, but compared to interstellar distances, it is almost nothing. Set against the 4 light-year distance to the nearest star, that habitable zone represents less than 1/trillionth of 1% of the gap between stars. A microscopic island of warmth, suspended in an ocean of cold. Earth exists within that narrow region. Every living organism on this planet depends on remaining inside it. Shift Earth just a few percent closer to the Sun and the oceans would begin to boil. Move it a few percent farther away and they would freeze. The margin is extraordinarily thin. The surrounding cold is immense. And if we zoom out even further beyond stars, beyond planetary systems, the structure of the universe becomes even more uneven. Galaxies themselves are not evenly distributed through space. They cluster along vast filaments and walls called the cosmic web, a structure shaped by gravity acting on the density variations seeded in the first moments after the Big Bang. Where filaments intersect, galaxy clusters form dense knots of thousands of galaxies bound together by gravity and surrounded by superheated gas. Between these filaments stretch cosmic voids. enormous regions of space containing almost no galaxies at all. These voids are the dominant feature of the universe's large-scale structure, and their size defies easy comprehension. A typical cosmic void spans 100 to 300 million light-years across. The largest known voids exceed 1 billion light-years in diameter. The Boötes void, one of the first supervoids discovered, stretches roughly 330 million light-years while containing fewer than 60 known galaxies in its interior. To put that emptiness in perspective, our local group contains over 50 galaxies packed into a region just 10 million light-years across. The Boötes void is 33 times wider and contains roughly the same number of galaxies. If Earth were located at the center of the Boötes void rather than within the Milky Way, astronomers would not have discovered other galaxies until far more powerful telescopes were developed. The night sky would appear almost completely dark beyond the stars of our own galaxy. Inside these voids, the density of matter drops to roughly 10 to 20% of the cosmic average. A few isolated dwarf galaxies drift through the emptiness, but they are so rare and so widely separated that you could travel tens of millions of light-years in any direction without encountering a single galaxy. No galaxy clusters form in voids. No rich stellar populations exist. Supernovae occur only rarely. The thermal environment inside a cosmic void approaches the pure cosmic microwave background temperature, with almost no local energy sources to raise it. Scientists estimate that cosmic voids occupy approximately 80 to 90% of the total volume of the observable universe. The filament, walls, clusters and galaxies where stars actually burn are confined to the remaining 10 to 20%. This means that if you were to choose a random location in the universe, the overwhelming probability is that you would find yourself inside a void, far from any galaxy, far from any star, surrounded by nothing but the 2.7 Kelvin glow of the cosmic microwave background stretching to the horizon in every direction. You would be drifting in a region colder than almost anything on Earth, darker than any night sky visible from our planet, and emptier than the best vacuum ever created by human technology. Even within the filaments where galaxies concentrate, most of the volume remains cold. Galaxies themselves are mostly empty space. The Milky Way's stellar disk is thin and sparse. Stars occupy an infinitesimal fraction of galactic volume. The interstellar medium, the gas and dust between stars, exists at temperatures ranging from roughly 50 to 10,000 Kelvin, depending on its state. But this material is so thinly distributed that its thermal contribution to the surrounding vacuum is minimal. Travel in a straight line through the Milky Way in any random direction, and you would pass through light-years of near vacuum for every brief moment spent within the atmosphere of a star. When all the numbers are considered together, they reveal a universe that is overwhelmingly cold. Stars are hot, but small. Accretion disks are hotter, but smaller still. Nebulae are warm, but diffuse. Planets are thermally active, but microscopic on galactic scales. Everything that produces or retains heat exists as a sparse scattering of exceptions within a cosmos that is, by volume, almost entirely at or near the 2.7 Kelvin baseline. The fraction of the universe that exists above temperatures like the freezing point of water is so small that expressing it requires scientific notation with extremely large negative exponents. Consider one estimate. The observable universe has a radius of approximately 46.5 billion light-years. Its total volume is roughly 4.2 times 10 to the power of 80 cubic meters. The combined volume of all stars, estimated at around 10 to the power of 24 stars, each with an average size somewhat smaller than the Sun, adds up to roughly 10 to the power of 51 cubic meters. Divide the volume of stars by the total volume of the universe, and you get a fraction on the order of 10 to the power of minus 29. That means the hot interiors of stars occupy less than 1/1000th of 1/1000th of 1/1000th of the total volume of space. Everything else is vacuum, existing at or near the temperature set by the cosmic microwave background. Warm matter is not just rare, it is almost non-existent when measured against the full scale of the universe. This is the thermal reality of the cosmos. The hot objects that dominate our experience, the ones that light up the sky, sustain life, and drive chemistry account for a share of the universe so small that rounding it to zero would introduce less error than many other uncertainties in cosmology. The universe is not a place where heat and cold compete equally. It is a place where cold has already won almost completely. Across nearly all of space and time, the intergalactic medium reinforces this picture. Between galaxy clusters, faint strands of gas stretch along the filaments of the cosmic web. Some of this gas is surprisingly hot, reaching temperatures of 100,000 to 10 million Kelvin, where gravitational shocks have heated it during the process of structure formation. This warm-hot intergalactic medium contains a significant fraction of all ordinary matter in the universe. Perhaps as much as 40 to 50% of all baryons. But the word hot here is misleading in a thermal sense. The temperature of a gas measures the average kinetic energy of its particles. A gas can have a very high temperature while simultaneously having an extremely low density. High temperature and low density together mean very little thermal energy per unit volume. The intergalactic medium may be technically hot in terms of particle motion, but it is so sparse that a cubic meter of this material contains only a handful of particles. Standing inside it, you would feel nothing, no warmth at all. It would be indistinguishable from a hard vacuum for any practical thermal purpose. Your body would continue to radiate heat into the void and receive almost nothing in return, regardless of whether the surrounding particles are moving at velocities corresponding to 1,000,000 degrees. This distinction between temperature and thermal energy is essential for understanding why the universe can be cold, despite containing extremely hot objects. Temperature is an intensive property. It describes the state of the matter that is present. Thermal energy is an extensive property. It depends on how much matter exists at that temperature. A single particle moving at a velocity corresponding to 1,000,000 degrees carries an almost negligible amount of actual energy. A room filled with air at 20 degrees Celsius contains vastly more thermal energy than a cubic light-year of intergalactic plasma at 10 million degrees. The intergalactic medium is hot in name only. In practice, it contributes almost nothing to the thermal environment of anything passing through it. This is why the universe can contain stars at millions of degrees, accretion disks at billions of degrees, and intergalactic gas at millions of degrees, yet still remain overwhelmingly cold. The hot regions are either too small or too sparse to matter on cosmic scales. The cold vacuum dominates not because it is powerful, but because it is everywhere. It does not need to overcome warmth. It simply exists in vastly greater quantity, and it does so by a margin so extreme that all the heat in all the stars, across all galaxies, amounts to little more than a rounding error in the thermal balance of the cosmos. The cosmic web itself illustrates this imbalance with striking visual clarity. Maps of the large-scale distribution of galaxies, assembled from surveys like the Sloan Digital Sky Survey that measured the positions and distances of millions of galaxies, reveal a structure that resembles foam. Thin, bright walls and filaments surround enormous dark voids. The bright regions where galaxies and clusters trace the scaffolding of the web occupy only a small fraction of the total volume. The dark regions, the voids, dominate overwhelmingly. Looking at these maps, you see a universe where structure is the exception, and emptiness is the rule. Filaments appear like delicate threads stretched across vast spaces of darkness. Galaxy clusters are small knots where these faint strands intersect, while the interiors of voids extend for hundreds of millions of light-years with almost nothing inside them except the fading afterglow of the Big Bang. It is a map of isolation drawn on the largest scale imaginable. Within those voids, the thermal story is simple and absolute. Nothing heats them except the cosmic microwave background. No stars burn there in meaningful numbers. No accretion disks flare. No stellar nurseries glow. No supernova remnants expand and fade. The void remains at 2.7 Kelvin year after year, century after century, across timescales that make the age of Earth seem brief by comparison. The cold in these regions is not temporary. It is not like a winter night that ends with sunrise. It is not seasonal or cyclical. It is permanent, the result of a universe whose initial heat has been stretched and diluted beyond recovery. These voids have not been warm since the first few 100,000 years after the Big Bang. And they will not become warm again. They represent the natural resting state of a cosmos that was once hot for a brief moment after its birth, and has been cooling ever since. Even galaxies themselves, when examined closely, are more like thermal deserts than glowing furnaces. The Milky Way is often imagined as a bright river of light, and from a distance, it does appear that way. But that brightness comes from countless individual stars, each one small and isolated. Between those stars lies cold, nearly empty interstellar space. The interstellar medium within our galaxy can reach temperatures of several thousand Kelvin in ionized regions and drop below 100 Kelvin in molecular cloud. But its density is so low, typically just a few atoms per cubic centimeter, that its overall thermal contribution is negligible. A galaxy is not a uniformly warm object. It is a collection of tiny, warm points embedded within an overwhelmingly cold background. And those points are vastly outnumbered by the empty space around them. The thermal portrait of the universe, then, is not a balanced mix of heat and cold competing for dominance. It is a portrait of almost total, overwhelming cold, interrupted by pinpoints of heat, so rare and so small that they barely register at cosmic scale. The stars are real. The heat they generate is real. The warmth they provide to orbiting planets is real. And in at least one case, it has given rise to life and consciousness. But measured against the volume and duration of the universe as a whole, that warmth is a statistical anomaly, a deviation from the norm, so extreme it borders on the miraculous. The question that remains is what all of this means. Not just for physics, not just for astronomy, but for our understanding of where we fit in the cosmos and what kind of universe we actually inhabit. The numbers are clear. The measurements are precise. The proportions are established beyond reasonable doubt. The universe is cold, nearly all of it, nearly all of the time. And the warmth that sustains us, the narrow range of temperature that allows liquid water, chemistry, and life occupies a fraction of reality so small it strains the limits of language to describe. What that smallness reveals about existence and about our place in a cosmos defined by cold and emptiness is the final step in this journey. Gather everything we have explored and hold it together for a moment. The universe began in unimaginable heat. It has been cooling for 13.8 billion years. The expansion of space stretched that original fire into a faint microwave whisper at 2.7 Kelvin, barely above absolute zero. Stars burn as local exceptions, intense, but tiny, scattered across distances so vast that the space between them remains overwhelmingly and permanently cold. Cosmic voids, spanning hundreds of millions of light years, sit at this universal baseline temperature with nothing to warm them. The fraction of the universe occupied by stellar interiors, the only places where new heat is continuously generated through nuclear fusion, is so small that it effectively disappears in any honest accounting of cosmic volume, and the fraction of space warm enough for liquid water, for chemistry, For anything resembling the conditions that support life on Earth is smaller, still so small, that expressing it in ordinary language requires stacking negative powers until the meaning becomes almost abstract. We have moved through this story step by step. First, we set aside the simple idea that space is cold in the way a winter night feels cold. Then we trace the origin of the universe's baseline temperature to the oldest light in existence, the fading afterglow of creation. And finally, we examine the hot exceptions stars, accretion disks, and glowing nebulae, and saw that they occupy only a vanishing fraction of the cosmos. Each stage revealed a deeper layer of the same truth. Now it is time to say what that truth actually means. This is the unsettling truth. Not simply that space is cold, that much is clear to anyone who has looked into a dark night sky and sensed its vast distance. The deeper truth is that warmth is rare. Staggeringly, almost unimaginably rare. The warm, habitable, life-permitting conditions we experience every day on the surface of this planet represent a cosmic anomaly so extreme that the universe, if it had a default state, would not recognize our environment as typical. We exist in a thermal outlier, a statistical exception, a small region of warmth set against an overwhelming background of cold. Its existence does not just invite explanation, it invites reflection. Consider what is required for Earth to be warm. First, there must be a star. Not just any star, but one of the right mass, burning at the right rate, producing the right spectrum of radiation to warm a rocky planet without overwhelming it. The Sun provides this balance with remarkable stability. Its output has remained consistent enough over 4.5 billion years to allow complex processes, including life, to develop on at least one orbiting world. A star 10% more massive would burn hotter and live shorter, possibly ending before complex systems had time to form. A star 20% less massive would emit most of its energy as infrared radiation, altering the conditions on any planet it warms. The range of suitable stars is narrower than it might first appear, and the star is only the beginning. A planet must orbit at the correct distance. Move it a few percent closer and its oceans could evaporate. Move it a few percent farther and they could freeze. This region, the habitable zone, is a narrow band where liquid water can exist on a planet's surface, compared to the full scale of a solar system. It is remarkably small, occupying less space than the gap between Jupiter and Saturn. Step outside that band in either direction, and the physics of water changes irreversibly. Too close, and it becomes vapor. Too far, and it becomes ice. Earth threads this needle with a precision that, from a cosmic perspective, seems almost unreasonable. Even within the habitable zone, distance from the star is not enough. Earth requires an atmosphere. Without one, the surface would swing between extreme conditions with each rotation, heating under direct sunlight and cooling rapidly in darkness. Much like the Moon, Earth's atmosphere performs a role so fundamental that it is easy to overlook. It traps infrared radiation through the greenhouse effect, redistributes heat from the equator toward the poles through convection, and moderates temperature differences between day and night. Without it, Earth's average surface temperature would be around minus 18 degrees Celsius, cold enough for the oceans to freeze. The greenhouse effect, driven primarily by water vapor and carbon dioxide, raises that average to about 15 degrees Celsius, a shift of 33 degrees that marks the difference between a frozen world and one capable of sustaining life. The atmosphere itself is the result of a very specific planetary history. Earth's mass had to be large enough to retain a substantial atmosphere against the stripping effects of solar wind, but not so large that it accumulated a thick hydrogen-helium envelope like Jupiter. Its distance from the Sun had to allow liquid water to persist, while avoiding the runaway greenhouse effect that transformed Venus into an extremely hot environment. Earth's magnetic field, generated by motion within its liquid iron core, had to be strong enough to deflect charged particles from the Sun that would otherwise erode the atmosphere over long timescales. Mars likely lost much of its atmosphere through this exact process. As its core cooled and its magnetic field weakened, the solar wind gradually stripped away its protective gases. Mars may once have been warmer. It is not warm now. When these conditions are considered together, a clear picture emerges. Maintaining planetary warmth over geological time requires a precise alignment of many independent factors. The right star, the right orbit, the right mass, the right atmosphere, the right magnetic field, the right geological activity to cycle carbon and regulate surface temperature over billions of years through a process called the carbonate-silicate cycle, where volcanic emissions add carbon dioxide to the atmosphere and weathering of silicate rocks removes it, creating a natural thermostat that has kept Earth's temperature within a habitable range through ice ages. Volcanic cataclysms and asteroid impact. The right amount of water delivered by comets and asteroids during the chaotic early history of the solar system, neither too much nor too little. The right kind of moon to stabilize axial tilt and prevent the extreme climate oscillations that would result from a wildly shifting rotational axis. Jupiter's presence in the outer solar system may even have been necessary. Its enormous gravity, deflecting many incoming comets and asteroids that would otherwise have bombarded the inner planets with far greater frequency. Each requirement is itself the result of a chain of physical events stretching back to the formation of the solar system, the collapse of the molecular cloud that formed the Sun, the supernova explosions that seeded that cloud with heavy elements, the generations of stars that lived and died before our own, the formation of the Milky Way, and the density fluctuations in the early universe that made galaxy formation possible in the first place. The chain extends across the entire history of cosmic evolution. Remove any one link, and the outcome changes completely. The warmth you feel on your skin right now is the final result of that chain stretching back through 4.5 billion years of planetary history. 5 billion years of stellar evolution and 13.8 billion years of cosmic expansion. None of it was inevitable. The laws of physics do not require a warm Earth. They allow it, but they do not demand it. The equations governing the universe are indifferent to whether any given planet falls within a narrow temperature range where liquid water can exist. The warmth exists because of how events unfolded, not because they had to. Now extend this perspective outward. Earth is one warm world, orbiting one stable star, in one region of one galaxy, among trillions. The Milky Way alone contains an estimated 200 to 400 billion stars. How many of those host planets within habitable zones? With the right mass, atmosphere, magnetic field and geological history to sustain warmth over billions of years? The honest answer is that we do not yet know. We have identified thousands of exoplanets through missions such as Kepler and the Transiting Exoplanets Survey satellite. Some orbit within habitable zones. A few are rocky and comparable in size to Earth. Data from Kepler suggests that perhaps 1 in 5 Sun-like stars may host a rocky planet within its habitable zone. That extrapolation would yield billions of candidates in the Milky Way alone. But confirming that a planet sits in the habitable zone is not the same as confirming it is warm in the way Earth is warm. Orbital distance is only the first filter. A planet can occupy the correct orbital distance and still be a frozen wasteland if it lacks an atmosphere, or a scorching hellscape if its atmosphere traps too much heat through an unchecked greenhouse effect, or a barren rock battered by radiation if it has no magnetic field to protect whatever atmosphere it managed to accumulate. Each additional filter removes candidates, Each requirement narrows the possibilities further. The number of truly Earth-like worlds, planets where surface temperatures remain within the narrow range that allows liquid water, complex chemistry, and long-term biological evolution may be extremely small. Or it may be moderately common. We do not yet have enough data to know. The James Webb Space Telescope is beginning to analyze exoplanet atmospheres, searching for chemical signatures that might indicate habitable conditions. In the coming decades, we may obtain the first direct evidence of whether nearby worlds possess the kind of warmth that matters. But even optimistic estimates suggest that potentially habitable planets represent only a tiny fraction of all planetary systems. And even those are only candidates. Many may turn out to be uninhabitable for reasons we cannot yet observe or fully understand across interstellar distances. Beyond our galaxy, the scale becomes even more daunting. The observable universe contains roughly 2 trillion galaxies. Each one holds its own stars, its own planetary systems, and its own narrow habitable zones surrounding isolated stellar sources. The total number of potentially warm worlds across all galaxies may reach into the tens of billions, a number that sounds vast until it is compared to the scale of everything else. The total volume of the observable universe is approximately 4.2 times 10 to the power of 80 cubic meters. The combined volume of all habitable zones around all stars is a fraction so small that even scientific notation struggles to capture its insignificance. The regions where life might exist occupy a share of cosmic volume that effectively rounds to zero, not because they do not exist, but because everything else is so overwhelmingly vast. This is not a flaw in the universe. It is a consequence of how physics operates on the largest scales. Gravity gathers matter into dense regions. Nuclear fusion ignites those regions into stars. Radiation from those stars warms thin shells of surrounding space. But only a small fraction of matter ever becomes part of this process. Most remain diffuse, spread across enormous distances, never forming stars at all. Most of the ordinary matter that does collect into galaxies sits in interstellar gas too thin to collapse. And even the matter that does collapse into stars heats only the thinnest possible shell of space around itself before its influence fades into the cosmic background. The universe is, in the most literal physical sense, a machine for producing cold. It was not designed to be cold. There is no intent, no plan, no purpose behind the thermal emptiness. It simply follows physical laws that, when applied to the actual distribution of matter and energy across cosmic volumes and timescales, inevitably produce a cosmos where warmth is the exception and cold is everything else. The laws of thermodynamics state that isolated systems evolve toward maximum entropy, toward the most probable distribution of energy, which is a uniform, featureless, cold equilibrium. Stars resist this trend locally by converting gravitational potential energy into thermal radiation. But they accelerate it globally by radiating that energy into the ever-expanding void, where it spreads out and cools. Every star that shines is, in a sense, moving the universe closer to its final thermal state. The very process that creates warmth in one place contributes to the overall dominance of cold everywhere else. Stars are, thermally speaking, secondary features, brillant, essential for the emergence of observers capable of asking these questions, but secondary nonetheless. The primary outcome of cosmic evolution is empty, cold, seal and space. Stars and their warm regions are a byproduct, a remarkable one, but still a byproduct. This perspective becomes even more striking when time is considered alongside space. The universe has existed for 13.8 billion years. Stars have been shining for roughly 13.5 billion of those years. Since the first generation formed a few 100 million years after the Big Bang, but stars do not last forever. The supply of hydrogen available for nuclear fusion is finite. It is being steadily consumed in stellar cores across every galaxy. And there is no known process that can replenish it once it is gone. When the hydrogen runs out, the stars go dark. The timeline of stellar extinction stretches across an almost incomprehensible future. Sun-like stars will continue forming and burning for tens of billions of years to come. The raw material for star formation, vast reservoirs of hydrogen gas distributed through galactic disks, is being depleted, but not yet exhausted. New stars still ignite every year in the Milky Way alone, roughly 3 solar masses of material collapsing into new stars annually. But the rate of star formation has been declining since its peak around 10 billion years ago. The universe is past its most active phase. The era of peak star formation lies behind us. With each passing billion years, fewer new stars are born than in the billion years before. Red dwarfs, the most efficient and long-lived stars, will outlast all others. Their internal convection mixes their hydrogen fuel thoroughly, allowing them to burn nearly all of it rather than just the core. The smallest red dwarfs may continue shining for 10 to 15 trillion years, roughly 1,000 times the current age of the universe. But even they will eventually exhaust their fuel. When the last red dwarf fades, no new stars will form. The remaining gas will have been used up or dispersed beyond the ability to collapse again. At that point, the universe enters what physicists call the degenerate era, a time dominated by the cooling remnants of dead stars. White dwarfs, the dense cores left behind when stars like the Sun exhaust their fuel, will slowly radiate away their remaining heat over trillions of years. They begin as intensely hot objects, sometimes hotter than the surfaces of massive stars. But they generate no new energy. They are embers, not fires. Over timescales stretching into quadrillions of years, they will cool from visible light to infrared, then to microwave wavelengths, eventually approaching thermal equilibrium with the cosmic background. Each one is a small-scale reflection of the universe's own cooling history, born hot, fading slowly, approaching but never quite reaching absolute zero. Neutron stars will follow a similar path, gradually losing their thermal and rotational energy over immense spans of time. Black holes will come to dominate the mass of the far-future universe, slowly evaporating through Hawking radiation over timescales that are almost impossible to comprehend. A stellar mass black hole requires roughly 10 to the power of 67 years to evaporate. A supermassive black hole at the center of a galaxy may take on the order of 10 to the power of 100 years, a number so large that writing it out in full would fill entire volumes. When the final black hole disappears in a faint release of radiation, the universe will be left with only diffuse particles and low-energy photons, drifting ever farther apart in an expanding space that continues to cool with time. When measured against this cosmic timeline, the era of starlight is a brief flicker. The stelliferous era, the period during which stars exist and shine, spans roughly 100 trillion years at most. That sounds like an eternity, and it is by human standards, but the eras that follow the long cooling of white dwarfs, the slow evaporation of black holes, the endless expansion of cold, empty space extend across timescales so much longer that the stellar era becomes almost negligible. If you compress the entire future history of the universe into a single year, with the Big Bang at midnight on January 1st and the evaporation of the last black hole at the end of December 31st, the entire era of starlight, all 100 trillion years of it, would occupy only a tiny fraction of the first second after midnight. The rest of the year, every remaining month, day, hour and second would unfold in darkness. At temperatures approaching absolute zero, the age of warmth is not just brief. It is so brief compared to the cold future that even calling it brief understates the reality. The universe will spend the overwhelming majority of its existence in darkness and near total cold. Stars are temporary. The warmth they provide is temporary. The habitable zones they create are temporary shelters against an enduring cold that will eventually reclaim everything. Every living thing that has ever existed on Earth or on any other world in any galaxy exists within this narrow window when the universe still produces light and heat. Before the first stars, there was only cooling radiation approaching the background temperature. After the last stars, there will be only fading remnants, cooling ever closer to absolute zero across spans of time so vast they defy comprehension. The present is a thin, bright interval between a cold past and an even colder future, a narrow line of light across an otherwise dark expanse. Earth itself is temporary. The Sun has roughly 5 billion years of stable hydrogen fusion remaining. After that, it will expand into a red giant, its outer layers extending beyond the orbit of Venus and possibly engulfing Earth entirely. The surface of that red giant sun will be cooler than it is today, but its enormous size will flood the inner solar system with radiation, rendering it uninhabitable. And long before that final stage, a more gradual change will already have made Earth unlivable. Stars like the Sun slowly grow brighter over time. As hydrogen fusion alters the composition of the core, energy output increases. In roughly 1 billion years, solar luminosity will rise by about 10%, enough to trigger a runaway greenhouse effect, evaporating the oceans and transforming Earth into a hot, dry world. Life on Earth's surface will become impossible. The warmth that has sustained biology for 4 billion years will become the heat that destroys it. Even the Sun's gift of warmth comes with an expiration date written into the physics of stellar evolution. Against this background of cosmic cold and temporal finitude, the existence of warmth on Earth takes on a weight that physics alone cannot fully convey. We are not merely warm. We are warm in a universe that overwhelmingly is not. We are warm during a cosmic era that will not last. We are warm on a planet whose conditions depend on a chain of physical factors, so specific and so fragile that altering any one of them would break the chain entirely. The warmth is not guaranteed. It is not permanent. It is not the natural state of things. It is a consequence of a particular star, at a particular distance, during a particular moment in cosmic history, and it will not last forever. Every sunrise is a small act of resistance against the broader conditions of the universe. Every ocean that remains liquid is a local exception to conditions that would freeze it solid almost everywhere else. Every living cell that maintains its internal balance is participating in a quiet struggle against the cold, a struggle that will not be lost through force, but through the gradual processes of expansion, dilution, and entropy. The second law of thermodynamics ensures that energy spreads from concentrated to diffuse, from hot to cold, from ordered to disordered. Stars temporarily concentrate energy through nuclear fusion. Life temporarily concentrates energy through complex chemistry. But both are local and temporary departures from a universal trend. That trend leads toward equilibrium. And at the scale of the universe, equilibrium means cold. It means the background temperature. It means 2.7 Kelvin and eventually even lower. The universe does not need to overcome warmth. It only needs time. The stars will fade. Warm regions will cool. The cosmic microwave background will continue to decline, and cold will remain stretching across every direction, across distances and durations that have no meaningful limit. This is not a reason for despair. It is a reason to notice. The warmth you experience right now, the narrow range of temperature that allows water to remain liquid, chemistry to function, and thought to emerge, exists within a universe that almost entirely lacks these conditions. You are reading these words on a world where the surface temperature sits comfortably between the freezing and boiling points of water. And that fact is so rare, at cosmic scale, that it deserves attention, not fear, not sadness, just recognition. The universe is cold, not in a local or temporary sense, but in a way that is nearly total. Around 2.7 Kelvin across vast expanses of space, approaching absolute zero in every direction beyond the small region warmed by nearby stars. The hot objects are real, they are powerful, but they occupy a fraction of the universe so small that, for most purposes, it disappears into the background. The warm places where liquid water flows and chemistry builds, and life thinks and wonders are rarer, still nested inside. Already rare shells of stellar warmth, dependent on planetary conditions that must align with extraordinary precision. The truth about how cold space really is comes down to this. It is not the number. It is not 2.7 Kelvin. That number is striking enough. But the deeper reality is the proportion. It is the realization that warmth, the condition you experience every moment of every day, the condition that makes your existence possible, occupies an almost immeasurably small fraction of everything that exists. The cold does not surround us the way darkness surrounds a campfire, with the fire holding back the night. The cold is the night. It is everything. And our warmth, the warmth of Earth, the warmth that sustains life, the warmth that allows consciousness to reflect on its own existence, is like a single flame burning in a darkness that stretches farther than light has traveled since the beginning of time. That flame is real. Its warmth is real. It has endured for 4 billion years, sustaining every living thing that has ever existed on this planet. But the darkness around it is vast beyond comprehension, larger than any mind can fully grasp, larger than any telescope can observe, larger than any number can truly capture. And that flame will not burn forever. Look up at the sky. See the stars for what they are. Each one is a source of heat pushing back against the same cold that surrounds everything. Each one creates a small region of warmth, a temporary exception to a universal condition. Some of those stars may warm distant worlds where other minds look upward and ask the same questions about the cold between the lights. We do not yet know, but we do know this. The warmth exists here, now, on this world, in this moment. It is rare, it is temporary, and it is ours. The universe is cold, almost all of it. Almost all of the time, but not here, not now.